Hello everyone, myself Dr. Sunny Kumar. I am an assistant professor in Department of Chemical Engineering, PKG College of Engineering and Technology, Panipat. I am giving a lecture on Chemical Engineering Thermodynamics 1. This is my lecture 5. You can also see the previous lectures. So in the previous lecture we have discussed about the internal energy and the first law of thermodynamics for cyclic process and the first law of thermodynamics for non-flow process, and we have read about the different professor which are the James, Pizul, H. von Helmholtz, or their setups, and the perpetual machine which never be stopped. Okay, so this thing we have read in the previous lecture, and we are also get the knowledge about the internal energy, basically the molecular vibrations, or uh, due to the molecular vibrations, or the atomic behavior of the uh, different atoms or molecules. So today we will discuss about the enthalpy and the constant volume and constant pressure, and examples of it, and the heat capacity. So these the four topics we will discuss today. So the first is enthalpy. So the enthalpy for a system kept at constant volume in which no work of expansion or any other kind of work is done, the change in the internal energy is equal to the heat supplied to it. When the system is free to change its volume, a constant external pressure, the change in internal energy is no longer equal to the energy supplied as heat. So as shown here, so in effects, a part of energy supplied is utilized by the system for occupying a new volume, and the energy thus utilized is equals to the work required to push the surrounding against a constant pressure. So the consequently this equation will be the internal energy is less than the heat. However, the heat is supplied at constant pressure can be measured as the change in the another thermodynamic property of the system, which we call enthalpy. So it is on at constant pressure, and the property we measure. So the enthalpy is denoted by H, as you have seen here, and is the most widely used of all thermodynamics functions. So it can be defined as you seeing this equation 1, this enthalpy is equal to the internal energy plus PdV. And this is a system, how the changes is happening in a system. So now here the U is the internal energy of the system, and P the absolute pressure, and V the volume of the system, as we have shown in the equation 1. So since U, P and V are all state functions, any combination of them also must be there a state function. So the enthalpy will be the state function which does not depend upon the path. The product of pressure and volume in equation 1 represent the work that must have been done against as environmental pressure P to create a volume V occupied by the system, or rather the energy that system possesses because of its occupying a space. Thus the enthalpy may be treated as total energy. So because it includes both the intrinsic energy poses uh, it possesses the internal energy and the energy due to the expansion possibility of the system. In differential form, if you will write the equation 1 in the differential form, so this is the representation: del H equal to del U plus del PV. So since all the terms in equation 2 are the state function, so it can be readily integrate to give, so this del change in enthalpy and change in internal energy plus del PV. So this is the three equation, and the equation 3 is applicable for any finite change occurring in the system. So we can show that the change in enthalpy for a mechanical reversible non-flow process at constant pressure is equal to the heat supplied. So the equation 2 can be expanded as, so like this you can easily expand dH equal to du plus p dv plus v dp. So the substituting, when you will put this internal energy equation, we know that del U equal to del Q minus del W. So into the equation 4, so what will happen? So we will get like this: dq minus dw plus p dv plus v dp. So the above equation you can simplify. Nothing that the dw equal to p dv for a reversible non-flow process. So where the at constant pressure process, so the dp, the change in the pressure will be 0. So the terms v dp will be the 0. So you can see that del this dh equal to differentiation of q will be equal for constant pressure process. So that is when a system is heated at constant pressure and only expansion works. Only the expansion works. The change in the enthalpy is equal to the heat supplied. For a process occurring at constant volume, so the work of expansion is 0. When it is at constant volume, so the work of expansion will be 0. So del U equal to del Q minus dW. That reveals that the change in internal energy is equal to the heat supplied. So this dW equal to the p dv, when the dV will be there is no change in volume, so that term will be 0. So then the internal energy equal to the heat supplied. So as shown, we have shown in this equation. So it is a for constant volume process. Internal energy equal to the heat. So now we will do some examples to understand the enthalpy and internal energy. So this is an example. The change in internal energy and change in enthalpy in kilojoule for 1 kilomole water as it is vaporized at the constant temperature of 373 Kelvin and constant pressure of 101.3 kilopascal. The specific volume of liquid and the vapor at these conditions are 1.04 into 10 to the power 3 and 1.675 millicube per meter cube per kilomole respectively, and this 1030 kilojoule of heat is added to the water for this change. So we have to calculate the internal and enthalpy of the system. So the expansion work done by the system during the vaporization. So what work done will be that W equal to P del V. So the expansion is happening from 1.04 to 1.675. So when you will write this, so you can get the work done will be, and the pressure is also given for this system, which is 101.3 into 10 to the power 3. So you will get the work done 169.57 kilojoule, and the heat is added to the water is given, which is 1030 kilojoule. So you can easily calculate the internal energy by using this equation, del equal to Q minus W. So when you will subtract the work done from the heat, so you will get 860.43 kilojoule internal energy for the system. And we know the enthalpy. So enthalpy, you know that internal energy plus del PV. So for a constant pressure, so it is given at a constant pressure. So this del which will be the PdV. So you will see the change in volume, we know that, and so 1.03 and internal energy we know 860 plus 169.57. So you will get 1.03 10 to the power 3 kilojoule enthalpy of the system. So this you will get it. So the another example we will discuss for the liquid carbon dioxide at 233 Kelvin has a vapor pressure of 1.005 into 10 to the power 3 kilopascal and specific volume of 0.9 into 10 to the power minus 3 meter cube per kilogram. Assume that CO2 is a saturated liquid at these conditions and its enthalpy is 0. So the latent heat of vaporization of CO2 is 320.5 kilojoule per kg and the specific volume of the saturated vapor is 38.2 into 10 to the power minus 3 meter cube kilogram. So we have to calculate the internal energy of the saturated liquid and the internal energy and enthalpy of saturated liquid. So these things we have to calculate for the liquids and the vapors both. So how to solve this? So we know that the internal energy of the saturated liquid is obtained as, so this is the formula. So we know that the H equal to U plus PV and the enthalpy is 0 saturated, where the HL is the enthalpy saturated liquid and VL is the specific volume. So enthalpy is 0, which is given, we are assuming. So we can easily calculate and the volume is 0.9 into 10 to the power 3 and the pressure is it is all 1.005. So you will get it the internal energy minus 0.9045 kilojoule per kg. And now the latent heat of the vaporization, which is del HV we get. So the for the vapor and enthalpy and the vapor for liquid plus the change in the del H, which is the latent heat of vaporization, which is already given 320 kilojoule per kg. When you will add it, so the enthalpy of the system is 0 for the liquid, and for the vapor it is already given, which is 320.5. So the vapor enthalpy will be 320.5 kilojoule per kg. So for the vapor case, when you will calculate the internal energy, so the formula will be the same. So HV minus PV. So HV we have already calculated, which is 320.5 kilojoule per kg, and pressure is also same. This is 1.005 into 10 to the power minus 3 plus 3, and thus volume of the this saturated vapor, specific volume of the saturated vapor is 38.2 into 10 to the power minus 3 meter cube per kg. When you multiply this, so you will get it 282.11 kilojoule per kg. This is the internal energy for the vapors, and minus 0.9045, it is a internal energy for the liquid, and enthalpy we have already calculated. So so now we will do the another example. This is an electric current of 0.5 angstrom from ampere, a 12 voltage supplies is passed for a 5 minute through a resistance in thermal contact with saturated water at 1 atmosphere. As result, 0.798 gram of water is vaporized. Assuming that the water vapor behave ideally, and calculate the molar internal energy and enthalpy change during the process. So we have to calculate the internal energy and enthalpy change for this process. So how to solve this? So the electrical energy supplied by the heater the water as heat. Since the vaporization is occurring at a constant pressure, it is already given. So the heat supplied to the water equal to the change in enthalpy. So the electric energy supplied, so it is a 0.5 ampere into this voltage, which is Vi, and we know the time, which is 5 minutes. So and we have to convert into the second, it is in minutes. So 5 into 10 60, and into multiply by 10 to the power 3. So you will get 1.8 kilojoule energy, electrical energy we will get. So if you will calculate the change in enthalpy, so 1.8 divided by 0.798, so you will get it 0.798, and so in terms of kilojoule per gram you will get. And if you want to convert into the kilojoule per mole, so you have all divided by the 18, which is the molecular weight of the water, saturated water. So so you will get 41 kilojoule per mole. This will be the change in enthalpy for this system. So for the constant pressure process, so we know the equation del H equal to del U plus P dV. So the assuming that the molar volume of the saturated liquid to be negligible compared to that the saturated vapor, so the del V is approximately equal to the molar volume of the vapor. Since the vapor behave ideally, so ideal gas law will be applied for the system. So P dV equal to the RT. R is a ideal gas constant. So you can easily calculate the internal energy. So the del H we know that, which is 41, and RT R is we know that it is a rate constant, which is 8.314 into 10 to the power minus 3, and the temperature which is also given here, and which is 373, because it is vaporized at 100 degree centigrade. So it will be the 273 plus 100, which is 273. So you will get 37.9 kilojoule per mole. So this is the internal energy for the system, and this is the enthalpy for the system, which is 41 kilojoule per mole. So now we will do the another example, a piston cylinder device which contains 0.1 kilogram of saturated water vapor that is maintained at a constant pressure of 400 kilopascal, and heat is supplied by the means of a resistance heater provided within the cylinder. So the current of 0.2 ampere from 230 volt source is passed continuously for 10 minutes. So the heat loss from the system is estimated 15.41 kilojoule. Making use of steam table, so determine the final temperature of the steam. So the solution, how to solve this? So heat supply by the electric heater. So we know that previously we have also calculated VIT. Where V is the voltage and I is current and T is time. So we know that the 0.2 ampere and 230 voltage, and time is this 10 minutes. So if you have to 27600 you will get it, and 60 is the you have to change into minutes. So 27.6 kilojoule heat is supplied to the by the electric heater. So the heat loss from the system, which is already given with a 15.41 kilojoule. So when you will reduce, this is the heat loss. So the net heat supplied is 27.6 minus 15.41, which is 12.19, which is used for the system. This heat is used for the system. So then in a constant pressure process, the heat supplied goes to the increase the enthalpy of the system. So the Q directly equal to the del H, which is 12.19 kilojoule. So the enthalpy of 0.1 kilogram gram of water vapor increase by 12.19 kilojoule, or unit mass of the change in enthalpy. So initially the system consists of saturated water vapor at 400 kilopascal, and from the steam tables the saturated steam, so this will be the 2738.6 kilojoule, and this enthalpy increase is 121.9 kilojoule enthalpy in the final state. So it is an initial state and it is the final state. So when you will get it, so the final state will be the 273.8.6 plus 121.9. So you will get it 2860.5 kilojoule per kg. So this will be the enthalpy, final state of enthalpy. So the enthalpy of the super saturated steam at 400 kilopascal, which is 2860.5 kilojoule per kg. From the table of the properties of superheated steam, the temperature of the steam is found 473.15. So now we will see the another example. So we have to calculate the internal energy del U and del H for 1 kilogram water when it is vaporized at a constant temperature of 100 degrees centigrade and the constant pressure of 101.33 kilopascal. The specific volume of the liquid and the vapor water at these conditions are 0.00104 and 1.673 meter cube kilogram per inverse respectively. For this change, heat in the amount of 2256.9 kilojoule is added to the water. So the solution is we have to take 1 kilogram of water as a system because its alone is of interest. So we imagine it contains in a cylinder by a frictionless piston that exert a constant pressure 101.33 as it is given, and as heat is added the water evaporates and expanding from its initial to final volume. So the equation for the 1 kilogram system will be, so the del H equal to Q, which is 2256.9 kilojoule. So the internal energy will be del H equal minus del PV, del H minus P del V. So this is we know, previously we know. For the final term, so PdV, so volume change we know that the 0.6163 and 0.001, so you will get 169.4 kilopascal meter cube. This will be this term you will get, and the internal energy when you will put this del H value and this PdV value, so the internal energy for the system will be 2087.5 kilojoule. So this will be the final answer. Actually in the previous question we have used the steam table, so that steam table we will discuss in the next lecture. So if you have any doubt for the steam table, so in the next lecture we will describe that one. So now we will discuss about the heat capacity. So the heat capacity of a substance is quantity of the heat to be supplied to a effect of a temperature rise of 1 degree. Okay, so thus the dq equal to C delta T, where C is the known as heat capacity of the substance, and this heat capacity of the unit mass of a substance is also known as specific heat of the substance. When it is a unit mass, then it will be the specific heat. So as you see in this cartoon, so heat capacity and how they are describe things. So I am not just lazing around, I am a conserving energy, and it is not sometime I do for fun. It is a law. So the heat capacity depends on the way in which the heat is supplied. So when the heat is supplied to a system at constant volume, so the system is unable to do any work. So the quantity of heat required is given by del Q equal to Cv del T, which is at constant volume, where the Cv is the known as the heat capacity at constant volume, and the constant volume heat capacity of a substance is defined as, so this is a heat constant volume heat capacity del Q upon del T at constant volume, and for constant volume, so del U equal to del Q minus dW. So where because it is the volume is constant, so this dW term will be 0. So you will get the Cv equal to del U upon del T, because del U equal to del Q, internal energy will be equal to the change in the energy heat. So if the rate is supplied to a substance at constant pressure, it is free to expand doing work against the constant pressure. As part, the heat supplied to the system is utilized for the work of expansion. So the more heat will be required, the rise of temperature than the required for a constant volume process for the same temperature changes. So the amount of heat required is related to the temperature rises. So at a constant pressure, when the volume is changing, so that the dq equal to cp dt. So that cp will be the heat capacity at constant pressure. So we have discussed the heat capacity for the constant volume and constant pressure. Constant volume it is cv and constant pressure it is cp. So you can write cp equal to del q upon del t at constant pressure. And for a constant pressure process, so we know this for equation del u equal to del q minus del w. So which is p dv minus v dp. So this v dp, the pressure is constant, and this dq will equal to the dh. So then, so this cp will del h upon del t at constant pressure. For a given temperature change, the heat required is more in a constant pressure than that in a constant volume process cp, which is greater than cv. So the heat required is more constant pressure process than the constant volume process. However, the difference between the cp and cv for solid and liquids are very small compared to the of gases. And the changes in the volume of solid liquid during the heating is not very significant. So the volume change is very not significant. So you can write, so internal energy will be cv dt at constant volume, and the enthalpy is cp dt at constant pressure. For a constant volume process, change in the internal energy, as we have shown this equation 21, and the internal energy is a state function, should gives the change in the internal energy in any process. This provided the initial and final volumes are the same irrespective of the path along which this change is brought about. So the heat required only for the process where the volume undergoes no change. The change in enthalpy in a constant pressure process or a process in which the initial and final pressure are the same. So it can be calculated or evaluated in the equation 22, and we can determine the heat supply in a true isobaric process. So today lecture we have discussed about the enthalpy at constant volume and constant pressure, and the examples of it, and we have discussed about the heat capacity and the specific heat capacity and the constant volume heat capacity and the specific heat capacity we have discussed. So in the next lecture we will discuss about the first law of thermodynamics for flow processes, and the mass and energy balance for open system, and examples of this. So thank you very much. If you have any doubt related to this lecture, so you can ask me. And this is my email ID, thechemicalsunnyrai@gmail.com, and this is my website. So if you have any query, so you can ask me or and contact me. Thank you very much.